Mm.
Hello guys. Let's start the lecture. Today we are going to learn about cryptography. Okay. Okay. Today we're going to talk about cryptography. How many of you are familiar with cryptography? What is the meaning of cryptography? Guys, are you able to see the screen? Are you able to hear me?
Yes, sir.
Yeah. Okay. Okay. So yeah, still sleeping. A lot of you are still not fully awake. So that's fine. So just have you heard of the cryptography? Have you heard of this term before? Have you heard of encryption, end-to-end encryption, encrypted, decrypted messages? Have you do you have any faint idea what it is? Cryptography, whenever I say somebody say cryptocurrency, for example, do you know what that means? Can anybody tell me a basic introduction of what cryptography means?
I think it's like when people sends messages to another people, sometimes they just use some codes
Yeah.
so that another person cannot like access that message or cannot do anything negative with that message.
Yeah.
So maybe
Yeah.
all
That's correct.
cryptography.
Yeah, Dipanjana, you are right. Like, so basically it is a way of sharing information without without giving access to everybody else. So you want the message to be private and secure, and that is how that is why the science of cryptography evolved. Okay, so let us say the today we are going to go deep into security and how cryptographic algorithms are going to be created, or we'll learn a little bit about um, the significant events like that, how the we'll first talk about a lot of terms, right? Like what is cryptology, what is asymmetric encryption, what is encryption. So we will talk about the fundamental terms that you need to be aware of. And when I'm telling you these terms, I want you to be really paying attention to these, because some of these terms will be asked for you in the examination. So I may ask you what is like, so these terms are very important. That's what I mean to say. And we will be, oh, okay, so we were, it's not, okay. Oh, it's not, I'm sharing the screen, right? Okay. So we'll be learning how to list and explain and explicate the basic protocols that we are using for securing our for communications. So we'll understand a little bit of what HTTP is and what HTTPS is, and we will also, maybe that will be covered in next week lecture. But cryptography is a huge science, so we will be dividing that into 2 lectures. So today we will be doing part 1, and the next week we'll be doing part 2. So we'll also be we'll discuss the nature and execution of the fundamental methods, like who designed some systems of cryptology and stuff of that sort. So if you look at cryptology, cryptology is a science of encryption, right? Like it combines basically cryptography and cryptanalysis. Although like cryptography and encryption based solutions, these are not application specific or security specific. So the encryption represents like a high level approach to security that we use today in extensively in all security systems. In fact, like many security related tools are embedded technologies that use this encryption, and they provide highly sensitive information that is handled by any kind of web application or an online application. So basically, how do we define encryption? Encryption is the process of converting an original message into an unreadable message. Okay, so using a key. So you take a message, you convert that message into what we call a ciphertext. I will talk about that a little bit later. So we convert that into an unreadable message for somebody who does not know, and that is called the process of encryption. The science of encryption is called cryptology. Okay, so cryptography is the process of making this possible, the process of making the codes to secure the transmission of information. That means the process of encryption and decryption, we call that as cryptography. So whenever you say graphy, what does it mean? Graphy, whenever you say graphy, what does it usually mean? Whenever you say calligraphy, photography, what does it mean? It relates to what? Graph
Art,
means
maybe.
what? It's like an image or an information, right? So something that is visual. So that is, so cryptography is something that was written in code. Written, crypto means like crypto means usually secret, right? And then graph, if you know Latin a little bit, graph is something like writing or an image. So that is how cryptography, the term cryptography has evolved. So now let's look at another term called cryptanalysis. So now this is about like kind of process of obtaining the original message from the encrypted message. So this is kind of like decoding, right? So you need to generate the message, and then you also need to decode. The end user must also need to decode. So we call that cryptanalysis, or we can call it decoding. So cryptanalysis is process of obtaining the original message from the ciphertext that you received. So, but this has to be done without actually knowing the algorithms. So we'll talk about algorithms. There are two kinds of algorithms that we're going to cover in this class. There are asymmetric algorithms and symmetric algorithms. And this, when you are doing cryptanalysis, you are not using any algorithms, but you are still trying to decrypt that message. So, and let us look at the basic definitions. Encryption is basically the same thing. It is about converting into an unreadable message called ciphertext. You take the original message, convert that into something that is not readable for unauthorized individuals. We call that as an encryption. So let us say if you say hello to somebody, then the ciphertext can be like XMPQRSWY, something like that. So that could be a ciphertext. Now that ciphertext can be sent to somebody, and that somebody needs to use the key in order to decrypt that message. So what is the process? What is decryption now? What is the meaning of decryption?
Converting a ciphertext into a readable text.
Yes, converting that back into a plain text, converting the ciphertext into a readable text. That's called decryption. So the foundations of cryptology, it has a long cultural history. Even during the times of kings, even during biblical times, people want to send messages to, long time ago, the kings used to send messages using messengers, right? They across different countries in relation to war, in relation to peace. So they use what we call cryptography, right? They use basic ciphers, and they send the two kingdoms like Greek and I don't know. I'm just telling different countries. This is nothing to do with history. So Greece want to talk to somebody in Rome, for example. So Greece wants to declare peace with Rome. So Greece will send a message, right? We don't want war, we want peace. So that can be that is a message that cannot be written clearly, because somebody who is sending that message, who is carrying that message using on a horse, or like a pigeon, whatever message, the form of communication it was used, if someone intercepts that message, they could actually misuse it. So what they usually do is, the two kingdoms can share a key saying that, okay, so every time I write a letter H, you convert that into letter W. Every time I write a letter E, you convert that into this. So that is, they share a key. And that's how the messengers doesn't have information about what that message is. They look at the message, only the kings or the relevant people, they have the message. So the cryptology has been existing, it has been in other forms, in layman's forms, way before computers and technology and all this blockchain technology came into existence. So don't think of cryptology as something really new and like this is a new evolved science in the last 10 years. No, it has been there. Have you seen, did you watch in World War II, there was a scientist who decoded the messages. Have you heard of that? German messages were decoded. There was a movie that was made about that as well. How the cryptology was used. I think I cannot recall the name of the movie, but it is a wonderful
Imitation
movie.
game.
Imitation game. Yes, Imitation Game. Watch that game. Watch that movie. It's a wonderful movie. It is a lesson on how we can encrypt, how you can decrypt. So Germans used to send these messages. This is like way before the technology of softwares and everything came into existence. They built he built a machine that decodes long messages. So, and they intercepted and shortened the war and saved a lot of lives. So it is there. the cryptology and cryptography were there even before the advent of computers. So it is an ancient science. But with the technology that we have today, we have the RSA algorithms, we have so much more. We have so much power to keep our data secure. But unfortunately, human intelligence has not evolved with the technology, and we still use the same passwords. And we use the same password for all the websites that we use. Wherever you log in, your phone password is the same. If you log in into 4 different websites, all your passwords are the same. If I crack one of your passwords, so all the passwords. So what I mean to say is human intelligence has not evolved, but the technology has evolved rapidly in the terms of cryptology and cryptography. So now let's look at the definitions. So what is an algorithm? So how do you define the algorithm, guys? What do you mean by an algorithm? So an algorithm is something that is used to generate a ciphertext. Okay, so you have a basic message. Hello, how are you? Let us say that is a message. Or meet me at 2 p.m. 2 p.m. in Rome or something, like, meet me at 2 p.m. today. So that is a message. So conversion of that message into an encrypted message, that is done by a formula, right? We can call that formula a key, or we can call that formula an algorithm. This is an encryption, right? The one that we are using, the algorithm or the formula that we are using to generate that encrypted message, that's called, or to generate that encrypted ciphertext, right? That is called an algorithm. A cipher, on the other hand, have you heard of the meaning of a cipher? What is a cipher?
Cipher is something which is confidential.
Yeah, so when we talk about cipher, like, what are you referring to? So you are talking about ciphertext, right? What is a ciphertext, for example?
It's a text which is converted to unreadable form.
Yes. So based on that, that's absolutely correct. Yes. So once you convert convert the original message into unreadable message, that unreadable message is called a ciphertext. Correct?
Yeah.
So what is from that? Can you tell me what is the meaning of a cipher?
It is something which is very confidential, very private, very secret.
Yeah, it is like a small part of the text.
Yeah.
Right? Cipher is like a small part of that large ciphertext. Right? It can be like a bits or bytes. It's like a small pieces of that large encrypted message. So, for example, there are 3 words, right? How are you? Let us say. So, how can be a particular cipher? And the text that can be used for this bit and this bit and this bit, like, these are individual components of the unencrypted message. So, and then what is a code? Code is again decoding. Whenever you see code is something that we use to transform larger components of a ciphertext, right? Okay, larger components of original text into ciphertext. So we are using code is similar to an algorithm. So in which an algorithm functions on a smaller level, but a code is something that used to create the ciphertext. So an algorithm can work on a smaller scale, but a code is a transformation of larger components like words or phrases at a larger scale of original message into an encrypted ciphertext. So that is called a code. An algorithm is a formula, and code is how you work with larger components. and how to deal with the spaces between the components. If you are sending a large volume of a paragraph, so the transformation of larger components like words or phrases into a single message. For example, love, right? You can put a symbol, so or you can say L or a small symbol. That large components can be encrypted into smaller components. So crypto system is all the transformations that are needed to convert this or all the transformations needed to create our ciphertext. So the set of transformations needed to convert the basic message into an encrypted message. That means what are all the things that you need to do. Sometimes it is not just enough to do one thing, right? If you say L replaced with A, E replaced with B, you can use some substitution cipher. We'll talk about the ciphers a little bit later in the same class today. But you can use more than one transformation, right? You can say whenever there is a C, you convert that to M and then go for the next letter of M. So we can use two or more transformations to create our ciphertext. So these definitions are pretty critical, and you need to understand, like, you know, go ahead and read these algorithms, read these terms, and hope you are clear on the basic definitions. Okay. The final exam, the question paper was going to be prepared very soon. The questions are going to be like 10 of the questions are going to be multiple choice questions. So in the multiple choice questions, you can expect simple questions like which of the following is a definition of a cryptology, and then there can be 4 definitions, and then you need to pick the right one. So this is a closed book examination, and make sure that you are prepared with the lecture slides. So if you prepare all the lecture slides, you will get full score. There is absolutely no issue with that. Somebody is chatting. Let's see what is it. No, it is not going to be online. It is going to be physically at a location because it is going to be invigilated. So it's not an open book exam. It's a closed book exam. Excuse me. It's a closed book exam. So you need to know the terms. We are not asking you to design an algorithm or something of that sort. We are asking you to understand the basics, whether you understood the basics of information security or not. That is what is going to be tested.
So physically invigilated means like our cameras will be on, right?
No. You will be coming to a physical location.
On campus, it will be on campus exam.
Yes. So the final exam is going to be invigilated on campus. Yes.
Oh, okay.
We will maintain social distance, because it is almost impossible for us to do this invigilation online. It's not possible, and there can be streaming issues and all this nonsense. So yeah. So last time the way we did it is all the people came at the physical location, and we organize the exam at the same time, and we will provide you the details of the exam very soon. Okay.
All
right. So let's look at the other definitions. So you probably know these definitions. Decipher means what? Let us see if you can get involved in playing a little bit of knowledge game. What is the meaning of decipher? Guys, decipher.
To convert the encrypted text into plain or simple text.
Yes, that is deciphering a ciphertext. That's called. What about encipher? Encipher. What does it mean?
Same like encryption.
Yes, exactly like encryption. To encrypt a message. Yes.
Yeah.
What is a crypto variable? What is a key? We will talk about the key a little bit later. What is a key? Key is nothing but the code that we use to create this encrypted message. It's like an algorithm, or it can be used along with an algorithm. Is a process. Algorithm is the method, but key is something that we can use to create that plain text, right? You can use different kinds of, you can use a public key or a private key. We will talk about those when we're talking about symmetric and asymmetric algorithms. Symmetric encryption, sorry. So the key is something that used along with the algorithm. The algorithm uses the key to change the original encrypted message into a ciphertext, and the same key can be used to convert that convert the ciphertext to an encrypted message. That is only possible in an in a symmetric encryption. We'll talk about the difference on the security level between symmetric and asymmetric encryption, which is the key for you to understand really. And a key space is the entire range of values, right? How many keys you're having? You're having A to Z, or like 0 to 1, 0 to 10, and then you have hash, pound, count, pound key, and then slash. What are the entire range of values that you can possibly be used to construct the individual key? So for example, basic key space can be A to Z in alphabets, 26 alphabets, and 0 to 9, 10 digits. That will be 36. And then you can use other things like hash and slash and minus, plus, whatever. Like these are different kinds of you can put all these things in the key space. So what are the range of values that you can be using to construct an individual key? Now, what is link encryption? These are the series of encryptions or decryptions between different systems, where each node decrypts a message that is sent to it and then re-encrypts it using the keys and sends it to another neighbor. So it is a series, right? So in this process, what it does is you can communicate along a different chain of people, or different chain of computers, without actually sharing without actually sharing the public key uniformly, right? So it's so the different keys. So let us say I am telling something to you, right? And you want to tell the same thing to your friend, and there are a few people who are listening outside, but they should not know what you are telling to each other, right? Let us say I want to tell to Deepa, and Deepa wants to tell to Amit. Okay, Amit wants to tell to something. So I'm saying meet at 2 p.m. to Deepa. I encrypt that message and send it to Deepa. Now Deepa wants to send the same message to Amit. Now Deepa can use a different ciphertext, can use a different key, different algorithm, and generate her own message. And then she send it to Amit. Now Amit got the message. Now Amit says, okay, this is ciphertext. Now he can decode that message, because she already knows. He already knows because he shared that with Deepa. Now the same thing can go on from neighbor to neighbor until it reaches the final destination. So this is called link encryption. You are working in a link. That means we are not sharing a public key and let everybody know about in the public about this. It is like think of it like when you are a kid, like you are in the back of a classroom and somebody wants to send it to the first person. Like how do? You send it to one person and the other person give it to other person, and so on. Like, are you familiar with this? Like, have you ever done this? You see it in the movies all the time, like, the way message is passed. So the way it is passed, that's called a creation of a link. The encryption of that is called link encryption. And plain text, you already know what a plain text is. What is a plain text?
Which is readable.
Which is readable, the basic message without that's the plain text. What is a stenography? So this is a slightly important concept that you need to know. So when you are hiding a message inside a picture, right? This is used to be like, if you see mystery pictures or like, I don't know, Indiana Jones movies, then there will be a small message that is inside a hidden document, right? So you open the document and then you see it in a different way. Then you find a letter G somewhere. Or you find like, the message is hidden inside an image. So this is called stenography. Stenography is actually a really older science. People used to send these messages using images to each other, because the other person who's looking at the message, if he's not very smart, he cannot even interpret that message. So the interpretation is sometimes subject to intelligence, but it is mostly now today we are using stenography to absolutely avoid any kind of intelligent interpretation. Like, even if somebody really intelligent looks at this message, he won't be able to understand today. But back in the olden days, when you are sending a message like as an image, if you are really smart, you may be able to deduct it. Okay, so this person is trying to tell this to this person. So that is something called stenography, hiding the message in a picture or in a graphic. That's called stenography. A work factor is the amount of effort that is required to perform the analysis on an encoded message. That means how much work you need to do. Like if I really put a lot of use a very complicated algorithm, very strong key, so I can create a very strong ciphertext that nobody can ever decode. But the problem with that is that, first of all, is it necessary that the message be so secure? Secondly, is it really worth the time that we are putting in? Sometimes people put a lot of effort into encoding the message, right? It may take hours usually to decode that message. So even computers, they may take a lot of message to decode that. So now we will explore like how robust, right, your algorithms and keys must be in order for you to be able to manage this effectively. So now we're looking at other cipher methods. So the plain text we can usually encrypt through. Okay, sorry. Yeah, a plain text you can usually encrypt through a bit stream or or a block cipher. We'll talk about a bit. You know what a bit is? Bits and bytes. Do you know that?
Binary codes, bits and bytes.
Yeah. So the memory code, we can transmit these, right? Series of these. So you can transmit in blocks, right? Bunch of bits. You can create a block and transmit that as a ciphertext, or you can transmit each bit separately, right? The bit stream is plain text where every bit is transformed into a cipher bit, one bit at a time. That means this bit is transformed into this, the next bit is transformed into this, and so on. That is a bit stream. That means you are creating cipher bits. Okay. A block cipher is divided into blocks, right? Set of 8 blocks or 16 blocks or 32 blocks, whatever the size that you want to transmit. So you take these big blocks and each is transformed into an encrypted block. So this is effectively larger for large paragraph transmissions, large text transmission. So we can use what we call a block. Block ciphers, they combine up to 8 to 16 set of 8 to 16 blocks, and each block is transformed into an encryption or a ciphertext. So basically, of course, this is for smaller linear streams, and this is for block cipher is for larger messages. You can use a block cipher. So the next one, and the most simplest and the age-old cipher that we can think of, is called a substitution cipher, right? Let us say a substitution cipher. Let me just give you a small example. Okay, let us see how creative you are. Okay. Okay, so let us say. Okay, let us say somebody types in. Oh, okay. So I'm not sharing that screen. Okay, unfortunately, I can't do. Let me see if I want to type or text message. Okay, so let us say. Okay, so are you able to see the screen?
Yes, sir.
Okay, so if this is a message, what substitution cipher did I use? Can you decode this message? I'm sending this message to somebody.
I love you.
I love you. That's correct. So I'm sending this message to somebody. Very good. Who is that? Who said that? Very nice. Very good decipher, right? So now, what substitution did I use?
One alphabet next.
One alphabet to
original
the next.
alphabet.
I created a one alphabet to the next, but you are able to guess it. I didn't tell you the key.
No.
You are able to guess it. Maybe that is because you are very, very intelligent. Or maybe it is something that is so basic that anybody can crack. Okay, so it is one of the most used passwords also. Top 10 used passwords. If you look at the top 10 passwords that were ever used, this is one of the top 10 used passwords. Let us check that if that is true or not. Let us see. Type in like in the Google top 10 passwords, right? So let me share that. So QWERTY, more items. Okay, so I can see 1 2 3 4 5 6 1 2 3 4 5 6 QWERTY. So because all the letters are together, password is a good password. 11111 ABC 1 2 3. So this is okay. Let's see more items. I think that is one of the most used passwords. Oh, okay. Top 20. Yeah, okay, fine. I think yeah, so I think it is so unhackable. Let us look at top 20 passwords. Let's look at top 20 passwords. Okay. Okay, so yeah, so you can see I love you is one of the passwords. QWERTY123 is one of the passwords. Dragon is one of the passwords. Sunshine is one of the passwords. Let me in. This is a very popular password. So at any point in time, have you ever used any of these passwords in the for your email or anything?
Many of them.
You have used many of them, so that means you are not very secure. So you just like the way somebody was able to crack my password. I just typed in JMFW. I typed in something. So people were able to guess that quite easily. Right? That's what the passwords are. Passwords must be generated so that they cannot be guessed. Right? But a lot of people, they do few mistakes when it comes to passwords. They want to use the same password for different logins. And that is not very safe. Okay, and we'll talk about the hash algorithms that we use. And do you ever wonder, okay, we'll talk about that hashing and a little bit those things a little bit later. Let me go back to the lecture. Let's finish this. So substitution cipher is this. Let's close this. Why is it not annotate? Clear all drawings. Okay, all right, that's good. The substitution cipher is a replacement of one value for another value. So monoalphabetic substitution uses one alphabet substitution, like you can replace A with X, C with D, or like whatever code that you want to use, whatever key you want to use, whatever algorithm. If you want to use like a process, like you can use that process. Polyalphabetic substitution, it's a little bit more it uses like one or more alphabets. It can like A and B can be, if whenever you see A and A, B together, you can see another two words together and so on. So polyalphabetic substitutions are slightly more complex, and it becomes like that much more difficult to decode. And the other one is Wigner cipher. So this is that uses like again polyalphabetic code. That means I will show you this Wigner square. Okay, this is a Wigner square. So you can use the code if you want to code A, right? In the first, you can use B. You can, like, let us say you want to use this line for your change, right? Let us say line 6 you want to use. So now you can say instead of A, you will write G. Instead of B, you'll write. So if I want to say meet me, right? Meet me at 2. Meet me at 2. So I will go to M. So let us say I want to share this key with you. So I'll say I shared number 9 with you. Say like, hey, Bijay, right? Bijay, I'm sharing number 9 with you. So now Bijay knows whenever I say meet me at 2, he will look M. M will be number 8, right? That will be U. And then E, I am going to encode that as M. And then E again, E. And then I will take T and then go to number 9 and C. So I'm going to send this text to Bidur or somebody. And then he can actually do the reverse, right? He can do, okay, so he's telling me M. So, okay. So the first one I got V, so that must have been M. And then the second letter he sent me was this M, so that must have been E. So then he can decode that using a polyalphabetic cipher. So now in this particular case, you can create whatever number you like. First word, like you can create like first word. If I'm sending a message, the first word use this one. The second word use this one. The third word use this one. See how much complex you can create this Wigner square. That's how you need to pronounce Wigner square. Do you understand how complex of code, how complex of cryptography we can do with a small square like this?
Yes, sir.
Yeah. So this is the advantages of Wigner square. We also have what we call a transposition cipher. So a transposition cipher is something that produces ciphertext that is highly difficult. So how does it work? It rearranges the values within one block, right? So if you want to say meet me, so that meet me at 2, let us say so it will say 3214, right? Then you say MEET becomes EMTE, right? So that can be the that can be transposition. That means you are just switching, right? Transposing the sequences of the code. So you can transpose the blocks also, right? You can transpose the words, you can transpose the letters within the words. Usually it can be done at any level, like at any, you want to do it at a character level, that means you transfer the letters or the characters, you can transport the words, you can transport the blocks, right? You can transport paragraphs also. But I mean, rearranging paragraphs doesn't make much of a sense, but transformation of words, right? If I write a text message to you, okay, if I juggle all the words, you will not be able to crack it, right? Right? If I send all the word, if I share a message with you, right, a lot of message, and then I share it by shuffling those words, and then give it to you, it will not make sense. You understand all the words, but you don't understand what I'm trying to tell you, correct? So that is called a transposition cipher. So if you can also shuffle in a transposition cipher, you not only can shuffle the words, but you can also shuffle the letters within each word. You can reverse the words, you can reverse the letters within the words. So you can do whatever transposition that you want. That is called a transposition cipher. Okay, so it can be done at any level. You can use it as strong a key as you want. You can use at a character level, or a word level, or a block level, or even at a paragraph level. Is that making sense, guys? Okay. Is that making sense, Venkat?
Yes, sir.
Yeah, Noreen. Yeah. Okay. So the other issue that we, okay, sorry, here. The other one is an XOR truth table. So how many of you are familiar with AND table, OR table? Have you learned any of these when you were, I don't know,
Yes, sir. In
10th
statistics.
grade, or where they, when do they teach you? Like
In 10th standard as well as in
okay.
intermediate to 11, 12 as well. Like
Okay.
if both the true, then answer is true in AND.
Mhm.
In or, if we need to have any one of the statement should be true to get the answer true.
Yeah. So okay. So where are these AND gates and OR gates usually used? What are the applications?
In digital signatures?
Yes, digital signatures. That is what we are using today, right? But
Okay.
what is the fundamental application of an AND gate or an OR gate? Where do you use an AND gate?
In signaling, sir?
Yeah, in signals, right? Like when you have two signals coming in, you want to give the green signal only if both of them are red, or both of them are like, or ones and ones. And then, so AND gates and OR gates are extensively used in building these complex transistors that we can use to generate code and building circuits. So all of this is basic electronic and electrical engineering that enables us to enjoy the tools that we are having today. So the logic gates are fundamental to electrical engineering, fundamental to how electronics work in the world that we see. Okay, so these are like a basic basic AND gate, OR gate, or like if I give 1 and 1, right, what would be the result of OR? If I use an OR gate, right, and I use 1 and 1 through it, what do you get?
1.
Yeah, if I use 1 and 0, then what do you get?
0.
1. You get 1.
In OR gate?
OR gate, yeah.
Okay.
1.
So if I give 0 and 0, what do you get in the OR gate?
0.
0. So, but what we are learning here is an exclusive OR gate, right? This is exclusive OR. That means only one of them must be correct, not all of them. So in an exclusive OR gate, what it is checking is if two bits are identical or not, right? If it is 1 and 1, it has to give 0. That is the difference between OR gate and exclusive OR gate. Is that being clear? So now let's look at basic OR gate. OR gate with 0 and 0, it will give 0, correct, right? If you look at a basic, forget about don't look at the bottom, just look at the OR gate that you usually know this OR gate. 0 and 0 is 0, right?
Yes.
0 and 1 is 1, right? 1 is 0, 1 is 1. and then you'll get 1. 1 and 0 is 1. But 1 and 1, in you have OR gate, you have, what do you have here?
1.
1. But in this XOR truth table, you have 0.
Okay.
That is the only difference. That means when 2 bits are identical, right? When 2 bits are identical, it gives you 0. When 2 bits are different, it gives you 1. Is that making sense?
Yes, sir.
Yeah. So this is the why do we need to use this? What is the advantage of this? So we use XOR gates. It is to check whether the cipher is a very simple cipher that is like where security is not a major requirement. Like you can check if you enter a password, like you can check whether this password is identical to the other password or not. So that means you can verify each and every letter and then you can check, right? So that is the advantage of an exclusive OR gate. Okay, so this is a truth table that you understand and everybody understands and everybody. Oh, sorry, I didn't show you this. This is the truth table, guys. I'm sorry I didn't show you. So 0 and 0 will give you 0. 1 and 1 should also give you 0. Why? Why 1 and 1
Identical.
are identical? That's the reason. It checks whether it is identical or not. Hello. Okay, let me mute everybody. Okay, I have muted everybody, and if you want to speak, you can unmute and speak. Okay. All right. So now next we are going to go to one of the most important breakthroughs in the history of cipher. Like this is done by AT&T. They use like a set of characters once per every encryption process. So the AT&T developed a cipher where the primary goal is you know what AT&T is like. It's what does it provide? What is AT&T? What is? Do you know? Have you never heard of AT&T, guys? Have you ever heard of AT&T? What is AT&T?
It's like a telco in US.
Yes, it is one of the biggest network service providers in US. They provide cell phone. They provide they provide cell service and they also provide internet. So it's one of the biggest. Like when I was in US, I used AT&T exclusively. I used that for the phone service and also for our internet is also powered by AT&T. So what they did, this was in 2000 only. I think it's not even, yeah. So basically what a Werner cipher is a one-time pad. Like, now today we have more technology like OTP and all these technologies. But a Werner cipher, it uses one use set of characters. That means it those set of characters are added to like the text that we want to send. So the resulting sum is then again converted into a text. So I'll show you with a small example. Let us see. So the pad values, what is a pad value? That means those are the values that you add, like you can add in either before or after the code. So each character of the plain text is then converted into a pad value based on the position where that is added. Then the resulting sum of the character is then converted back into a cipher letter for transmission. So let us say I want to sell meet me at 3, right? So I want to add a pad value for this, like so I can add 3, let us say. So m plus 3, e plus 3, e plus 3, t plus 3. So I created a pad value. So I padded it. I padded the letters with one character that I want. So the resulting sum, that m plus 3 is what? M N O P. So I'll put P. And e plus 3 is G, right? 3 G G. And then I created a new word that is padded with the value of 3. Now this value can be changed. I can pad with any other value. I can pad it with 4, I can pad it with 5, but you do not know what I padded with. So that is how it is. AT&T created, but sometimes the values will be more than 6, right? If I padded with y, if I padded y plus 3, what is y plus 3? What is y plus 3, guys? Y plus 3. How do you convert y plus 3?
Maybe it's B.
It's B, because it is more than 26. You got to go back to the list again, right? Then it is, so now y plus 3, y is 25, right? 25 plus 3 is 28. So if it is 28, what I need to do is divide by 26. 28 divided by 26 will give me how much of remainder? 28 divided by 26 will give me a
2.
remainder of what?
2.
2. So the 2 is represented by what letter?
B.
B. So that is how a Varnam cipher is going to be designed. Is that making sense to all of you?
Yes.
Yeah. So these ciphers are pretty basic, really. Like, even before the the one that we talked about, the other ones that we see in Indiana Jones movies. I don't know how much of English movies you watch. Like most of the Indiana Jones movies are like exploring something, finding something, decoding something. You guys watch any of those movies like that? Do you have like in your country, do you have messages? Do you have movies that have decoding game or treasure hunt? Have you played any games like that before? Does anybody have experience in playing the games like that? Huh? Share your experience if you have any experience with. So basically, these are all based on fundamental ciphers, and see, that's why ciphering is all about thinking out of the box, thinking intelligently, outsmarting your opponent. So outsmarting, that's why hackers are actually very smart. They think very mathematically. They think extremely logically. And if you ever want to improve your ability to think and comprehend numbers and use complex logic, try and thinking of becoming like an ethical hacker. You're working for the government. Like you can work for the government, like doing ethical hacking. Like some enemy sends messages, right? Like today we have only one enemy. Who is that enemy? Australia has only one enemy. Who is that enemy? You don't know. Okay, so if we get some message was transmitted from one country to another country, and you want to decode that message, right? You can do what we call ethical hacking for the government, right? So as the ethical hacking, as the word says, it is based on decoding danger, right? That's the same thing in the imitation game. It's the same thing. It's called the imitation game. So it uses the text in the book, like the book cipher is like having a book. Like let's say you have a book. Let me take a book. Yeah. Okay. Let us say you have a book. A book cipher. Let us say this is a Bible. I think of this like a Bible. A book cipher will use the code. For example, if I use X. If I use 23, right, then I am going to go to 23rd page and look at the first letter in the 23rd page. Are you following? So what the book cipher does is, unless you know what book I am using to cipher, you cannot decode. Is that making sense? So I'm sharing MEET or something like that. Okay, now meet me at 3, let us say that message. So you got this message. Now you know how to create a cipher using that book. So the ciphertext will contain the page number and the word number and the column number. So it says like, so the first letter, instead of writing M, I will say, so M is available in 23rd page on the 5th line on the fourth letter. So I will say 2347, right? That's the number that I will write. So now you got the message, right? Now you got this 2374. Now the person who is using the key, they will say, okay, what does he want to say? He wants me to go to 23rd page, and then you got to go to 4 and then 7. Now he knows the first letter is M. Is that making sense?
Yes, sir.
Yeah. So book ciphers are very common, especially the most used books that use for ciphers are Bibles, right? You see Bibles primarily, like the Old Testament was used to be very, very widely used all across the world, so that Bibles were used as like a cipher. People always use this, open the Bible and see, okay, what is this trying to tell me? So that's a book cipher, or we can also call it like a running key cipher. So the algorithm is mechanically processing of looking up what particular reference it is there, right? So then we can convert that back into ciphertext. And then let's come to hash functions. Before we do, let me just let's take the attendance right away. Okay, let me finish it and then I'll take the attendance. Okay then. Okay, what is a hash function? What is the meaning of a hash function? Have you ever heard of hash function before? What is the purpose of a hash function? Just give me 1 minute, I'll be back. Think about it. All right. Okay. Do I have an answer? What is a Meniere square? I mean, sorry. What is a hash function?
Mapping data with address values, fixed size values.
Okay, mapping data with address values.
Address values in the system. Yeah.
Okay. So how is a hash function generated in that case?
It's like in a system we are having addresses like a fixed arbitrary size 01, 001, 01, 02, 03. Some addresses will be there. We'll map the data to that address.
Okay, that is one way of hashing. That's correct. So okay, so what can we what is the difference between encryption and hashing? Like which one is more secure, you think? Hashing is primarily used on passwords, Okay, so you seem to be a little bit more knowledgeable about information security. Can you see how? Can you tell us how hashing is used to verify whether the password is right or not? You're correct. Like you are almost like you're 100% right when you said that. Umulwara, right?
Yes, sir.
Yeah. So hashing can be used to secure passwords, right? To verify passwords and to check whether. So hashing is primarily used in conjunction with passwords. So do you know the mechanism that is behind that technology?
No, sir.
No? Okay. Bijay, yeah, Bijay, you raise your hand. And do you want to share?
I'm not sure if this is correct, but while verifying the password, the hash of the original password is saved somewhere in the system, and when a user puts his password, hash is calculated, and those two hash values are compared, and if they match, I think that is how password.
Perfect, Bijay, perfect. That is 100% right. So why do we need this hash? Why can't we just save the password?
Because we can't store the plain password.
Why not? Like, let us say I'm sending. Okay, I have a. Does anybody have like what website do you use, Bijay? What website like you use to log in? Like, do you have an online?
Facebook.
Okay, you forgot like your password. Like you want the way. Do you think Facebook knows your password?
They store my password, but not in plain text. They encrypt or they generate some hash values and they save in the database.
Yes. So Facebook is not allowed to know your password, even though you are using Facebook. It is illegal, right? So what Facebook does is when you say when you have your own password, your birthday or like you created a complex password, it hashes that. A hash is something that is allocated to that particular password. So even if your password is only 4 characters long, it generates a hash that is large enough for the user, for the one who is stealing the message to get confused. So when you are talking about encryption, a 4-letter word can be translated into another 4-letter or maybe 15 or 16-letter code, but not with the hash, right? A hash can store a paragraph, a letter, or a word with a cipher of the same length. Is that making sense? So let me show you using a small demo. Okay, so are you still sharing the screen? Let me generate hash. Okay. Generate hash. No, generate hash function. Yeah, generate hash password. Okay. So now, let us say if you are you seeing the screen? So let us say June 19, 2020. Let us say if I type in that word and I ask it to generate. So now you can see the hash that is generated, right? Are you able to see the screen? So this is what the Facebook will store, right? It does not know my password. So if I forgot my password, right? What will it do? Will it tell me, hey, I know your password. Your password is June 19, 2020. Will it be able to tell? How many of you forgot your password and you called a company saying that, sir, I forgot my password? How often were they able to tell you the password? Can you even recollect from
They can't tell the password.
They can't tell you the password because they don't know. They honestly do not know. If they know, that is illegal. You can report that to the police. If they say, oh, okay, you forgot your password, I know your password. Let me tell you tell me your password. That's not how a password function works, right? Everybody is aware of that. So how does, let us say you put in your birthday. Let us say you're born on June 19 in Nepal or like in India. All right. So you created a password. You can create as long as password hash code as possible. So even if you type in just JK MNOP, right? This is not a secure password, but you see how long this is hash. This is what the Facebook will show. Even if I type in like a lot of characters, right? The hash length is not increasing, as you can see. Do you see the hash length? It's the same length. This is not how an encryption will work. This is how a hash will work. Is that making sense to everybody? So no matter how long or how short my password is, my hash is long enough for somebody who is trying to crack it. They cannot take a look at it, and they first of all, they don't know that that is a real password. They don't know how long that password is. When someone sees an encryption of 4-letter word, right, they may say, okay, this is a 4-letter word, let me crack it. But when they see a hash that is 20 letters long, they do not know whether my password is 4 letters, 15 letters, 20 letters, or 40 letters. They cannot know that. Is that gives you an additional layer of security when it comes to password verification. So even if you're but there is one danger with hashes. Can you predict that can you predict that danger? Can two passwords have same hash? Okay, so one of them is QWERTY, right? I type in QWERTY and this is my hash. Okay, and I type in Apple, like that is another hash. These hashes are randomly generated. So it is possible, technically possible, right, that the hash may be the same for both the passwords, but it is highly unlikely. Are you following me, guys?
Yes,
Yes, sir.
Yeah. So the hash can be even the longer hash. This is basically how a password or a hashing works. I hope that is clear. Okay. A hash function is it is used for password verification systems. So whenever you forgot your password or when you're entering your password into a system, that's how a hash function will verify whether okay, let me go back to the lecture. Okay, so now you can see are you able to see the screen? Okay, so that's a hash function, by the way. So it's basically generation of hash function. We can use fundamental type of hash function like MD5, MD4. So different levels of security that we want to use. So we can use a text convert the data like into a different format using like different key. What is the size of the key that you want to generate and how many characters you want to use. So like it's a generation of hash, right? So now the cryptographic algorithms are often grouped into like two broad categories. So this is where the crux of your cryptography skills is going to be. So we will learn about symmetric algorithm and asymmetric algorithm. Today's most popular systems, they use a combination of these two, right? We call them hybrid algorithms. So symmetric algorithm is one of the simplest things to follow. Let us look at symmetric encryption. Asymmetric encryption is the same key for, like, let us say I use a key to encrypt my message. I share my key. Let us say I want to share my message to Noreen, like, Noreen wants to receive message from me. I create a ciphertext using my key, and I share with Noreen the key that I want. So Noreen can use the same key to decode the message and understand my message. So very simple. It's only one key that is involved, and the key is a shared one. I can share the key. I can share the key with Noreen. But let us say there is somebody else who wants to eavesdrop. They want to understand what I'm trying to tell to Noreen. And let us say Bidur. Bidur is interested. Bidur is a hacker. Bidur wants to see he was able to get that key. All right. So what happens? So Bidur is able to decode what my message is. Right. So this is the issue with the symmetric encryption. That means if the key is leaked out, right, the message is also leaked out. Okay. If he sees the message and if he knows the key, then there is no secrecy. Is that making sense? So both the sender and the receiver must have the encryption key, and if they are sharing that key also, right, somebody can see that key. So that is how a symmetric encryption is easy to do. Is the simplest one to do. Is easy to follow, but it posed a lot of security challenges, right? So back in the day, in before the RSA algorithm or asymmetric encryption was discovered, we will talk about RSA algorithm and asymmetric encryption in a while. So this is how this is the most security that we can provide with the technology that we have, and with that comes the risk. So the key, if the key is leaked out, the message is also leaked out. So that is the problem with the symmetric encryption. So if the copy of the key is compromised, then we don't have security. For that, let us see. Let us understand the same concept. Like, let us say I am sharing. Let us say Rachel at ABC Corporation. She generates a secret key, and she tells Alex that key. So this is the key that we need to use to decrypt my message. So she sends a message, right? The deal is a go, right? This is like a business deal. The deal is like, we are happy with the deal. It's a very important message, right? Obviously, it's like a contract or like a bid. So it's a very important message that needs to be securely transferred to Alex. So now she uses the key to encrypt the message, and she generates this function, generates this message, and she sends this message to Alex. So Alex knows this key. Alex and they use the same key, guys. Right? Alex uses the key and gets a message. So what is the problem with this? Where is the security issue? What is the security issue? Ricky, Gautam, Noreen?
If someone wants to know the key, they can hack the key, sir. If the key is hacked, then there is no secrecy. Like
There
they're
is no
sharing only one key.
Yeah,
There is
because
no public and private key.
there is only one key, and it is as safe as the key. As long as the key is secure, it is safe. But if the key is compromised, then you don't have any security coming from it. So that is the major issue. It was even like, the so the level of security is symmetric encryption. It uses different levels of security. Okay, sorry. I did not show the message. So this is how, if EA is, so this is the private courier, and then the deal is a go. Let us say that is converted into a ciphertext, and then the same key is used for the next one, right? So the symmetric encryption, there are different standards of symmetric encryption. So one of the most popular crypto systems, it uses like a 64-bit block size. So it depends on the level of security. National Institute of Security and Technology, and these they created, like, whenever you are sharing information through a key, so there has to be some encryption standard, like we call it like a triple DES or AES, advanced encryption standards. So basically what these standards are, you don't need to know in detail what these standards are, because that is beyond the scope of this lecture. But these are all the standards, like how secure do you want your key to be? That's all. Like, the larger the block, right? The larger the block size, the larger will be the level of security that that it can meet the NIST standards, National Institute of Security and Technology. So then, because we had the issues with symmetric algorithms, symmetric encryption algorithms, now we have discovered, like, this was asymmetric algorithm that was discovered. It was in the 19th century. Okay, so this is a revolution, really. This is the RSA algorithm is how, like, if you can convert the advantage of an RSA algorithm is you can convert an encryption message into a ciphertext, but the reverse process is very difficult. That is the logic, right? So how can I send a message to, let us say, Bidur, right, using a key, and the reverse process of conversion of the ciphertext to this is almost impossible, no matter how hard he tries, no matter how hard it is. So that is the idea behind an RSA algorithm. RSA, R, S, and A, these three numbers stand for three different scientists who created who developed this algorithm. I think it's a good respect for us to learn the names of the scientists as well. So RSA algorithm founders, algorithm who was found. Okay, let us. So who found this? It was done by Rivest, Shamir, and Adliman. Those are the names that stands with RSA. This is the algorithm that modern computers use, right? This is the heart. This is the, like, when you're using Bitcoin, when you're using bank accounts. So you owe your security to these three gentlemen here, Rivest, Shamir, and Aldiman. So they use this algorithm to generate, to make the reverse process of conversion of the ciphertext to original message almost impossible. It will take for an intelligent computer 100 years for an intelligent super fast computer to decode an RSA algorithm by luck. 100 years it has to work to get that message. If you make it more complex, it will be even more impossible for you to decode that reverse code. So what is the technology that is used? Let's look at the technology that is being implemented by the RSA algorithm, or asymmetric encryption. So asymmetric encryption works using two different keys, right? We are using not just one key, but two different keys. Either key can be used to encrypt or decrypt a message. So you can use either one of the keys to encrypt or decrypt a message. If one key encrypts a message, only key B can decrypt that message. Okay, so the highest value where one key serves as a private key and the other one can be a public key, because I can share the, okay, so let me show you this. Okay, so look at this very carefully. Now you have public keys that are stored over here, right? So now, sounds great, thanks, is a message that wants to like, let us say Alex wants to send a message, right, to this. So Alex wants to send a message to Rachel at ABC Corporation. Rachel stores her public key where it can be accessed by anyone. So this is a public key that Alex can use, right? So he uses, she shares, hey Alex, oh, you want my key? So this is my public key. Use that to encrypt the message, right? So Alex uses that key to encrypt a message and sends this ciphertext. Now let us say Bidur is somebody who is an ethical hacker, right? So he looks at this and says like, what is this? How can I decode it? Then he looks at the public key, right? Now, even if he looks at the public key, he cannot like understand. right? He knows the public key. The public key is known for everybody, right? Even if he looks at it, oh man, I can't even figure out. I see, because the reverse process is extremely difficult, right? That's what RSA algorithm does is. So unless now this message is going to Rachel now. Now Rachel has the key. She does not share with Alex her private key. So she uses the private key to decode the message. So the person in the middle who sees the information, who knows the key, can do nothing about it. Is that clear?
Yes, sir. Sir, so the private key should be shared by both the person?
No. The private key is your own private key.
Okay.
Alex doesn't know his private key, her private key. No. So the private key is private. But if somebody gets access to your private key also, then it's a trouble. Then there is no security. Right? So if somebody have access to the private key also, then that person can also use that private key on this message. But the reverse process, but the public repository doesn't have the private keys of individual people. Now Rachel wants to send a message to Alex. Rachel says, hey, Alex, send me your, where is your public key? And Alex says, okay, don't worry, here is my public key. And Rachel encrypts that message using Alex's public key and sends it back to him. All right? Somebody in the middle is looking at both the messages. Like he looks at the message, he looks at the key. No problem. But he cannot do anything about it. Because he knows because he doesn't have the private key. So even she doesn't know Alex's private key. Alex doesn't know Rachel's private key. Do you see how beautiful this is?
This is super.
Yeah, this is what the revolution of RSA algorithm does. The mathematics behind it is so complex. Like, it's not too complex. I mean, let me take that back. It's not too complex. You can understand it. Like if you are interested, I understood it. Like it took me 15 to 20 minutes to really code and create that algorithm, but it is really beautiful. Like I will tell you, like if you are interested in hacking or security, I'll strongly recommend you to learn a little bit more about information security. Anyway, so yeah, so I'll share with you one website in the tutorial class. I'll share. Okay. In the tutorial class I can share. Okay. So today's tutorial class is going to be very, very interesting. I'm going to share a few details. A few details of different websites, and we'll play a game. In the next week, we're going to play a cryptography game, I think.
Excuse
by
me,
the
sir,
way,
could you please mention those websites in the Moodle, because I am in the different tutorial, but I am interested.
Okay. I cannot tell you what to do, but like I think Gangson will also cover some of these concepts, but his style may be different, but
Okay.
yeah, but he also covers most of the
Okay, that's okay. That's fine. Thank you.
okay, because I cannot talk on behalf of other faculty, so they are
Sure.
their style is different, my style is different. So encryption key size is a key, but you are more than welcome to join my class. I am not I am not going to restrict you from coming to my tutorial class. If you are interested in learning a little bit more, or like learning, if you like my style, I don't know, it's up to you. But I mean, and also my students, if they want to go, they go to Gangson's class as well. There is no but if you want attendance, like come to the class that you need to go to, right? If my students go to Gangson's class, I don't mind. I don't have any problem with that. And I will give attendance only if you come to my class during my class, right? You cannot say I attended his class, give me attendance. Please don't do that, because it unnecessarily complicates things for us. So you can attend any class. As long as you are willing to learn, you are more than welcome to join my class. And yeah, I cannot provide you attendance if you are not enrolled in my class. Okay, so that's out of the way. For crypto systems, security of data is not depending on like encrypting algorithms. That's the whole idea, right? Like even, okay, do you know how secure these algorithms are? You will be really surprised to see, like if you have an 8-bit length, right? A computer can crack it in like nanoseconds, 0.43 nanoseconds, right? You may think like, you know, if you have high speed processing power of a computer, you have an 8-bit length data, right? It will take 43 seconds. But as you increase the number to 16, if you have 16 length, 16 bits, then it becomes slightly more complex. You are going into milliseconds. Still very quick. Computer can still crack it, right? It will take you about like 22 milliseconds to crack. But as you are increasing to maybe 56-bit, right? The difference, the why instead of 32-bit to 42-bit, 32 to 64, there is a number called 56 in the middle. Why? Can you imagine why this number was introduced, 56 bits? Because it is not a standard 2 to the power something, right? All the other numbers are 2 to the power something. 2 cube is 8, 2 power 4 is 16, 2 to the power, I mean, not 24 by 2 to the power 5 is 32. But this is the, if you look at 56-bit, this is not 2 to the power anything. But why is it introduced here? Because it provides the security that is enough for you. But if you have a 32-bit, it can be cracked within like 72 milliseconds. Less than a millisecond, I mean 72 milliseconds, you can crack it on average. Or you can take a maximum of 143 milliseconds. 1/10 of a second you can take, right? But if you are using a 56-bit, if the key length is 56-bit, then it becomes days. It becomes so complex. The number of guesses that you need to make to guess that key becomes so complex that it does not worthwhile the time. Okay, but some people are not even happy with the 56-bit security. 28 days, maybe people will be, if it is like a secret service talking about war, planning a war, maybe 28 days is worth it. Maybe they will take 28 days and figure it out, right? Maybe it will take, on average, it will take less than 28 days, by the way. But if you make it a 64-bit, right, then it will take 20 years to guess that key randomly. Becomes almost impossible, and it is not even worth trying. Are you able to see the magnitude of the growth? How this is growing exponentially? How this number of guesses that you need to make is growing exponentially, right? If it is only just by doubling it from 8 to 16, you changed just from 32 to 64. You see the difference. The difference between a 32-bit security and 64-bit security. What is the difference between a light and day? Where is 0.072 seconds, 72 milliseconds and 9.7 years? You see how different this additional 32 bits of security is going to give you? The layers of security. Are you able to follow? So the encryption key grows exponentially, and it makes it impossible as you increase the length of the key. Okay, the length of the key must be long enough for you to assume the level of security. Usually a 32-bit is not sufficient for most security purposes. They use a 64-bit encryption or 56-bit at least. 56-bit you can use for, like, you know, 56-bit key length for, obviously you can use financial services and like, those, I mean, people doesn't take 28 days to crack a particular thing, but most of the time you can use a 64-bit and you can be assured that like, nobody is going to spend 19 years to crack a particular key, right? So is that making sense, guys?
Yes, sir.
Yeah, but if you use a 512-bit, it will take you more time to crack it than the time 14 trillion. This is like how many years? This is not even like, this is like 10 to the power 100 times than the age of the universe, right? It is impossible. Just you can say it's impossible to guess the password, to guess the key. So guessing the key is so difficult. Making the guesswork of the key so difficult eliminates the hackers. Hackers will only be interested if it is only a 32-bit. Maybe they are interested to crack it. But once you change that to 56-bit and 64-bit, no, they will not be investing any more time in trying to crack your key. So that means your public key is secure enough. Okay, your public key, even though the public key is there, he cannot deduce what it means. Right? That's the power of an RSA algorithm. So basically, we learned quite a lot today about. I mean, I don't know how you define it. Hopefully, you understood what cryptography and encryption provide. So I hope you guys are quite comfortable with what you have learned. Are there any particular questions that you want to have and that you want to ask me?
Yes, sir. I have a question.
Yeah.
So you were talking about Alex.
Okay.
That the Alex even doesn't know about the password.
Yeah.
And
Okay. So this one. Yeah.
there's been an algorithm.
Yeah.
It's like there was kind of matching, right?
Yeah. Yeah.
So what if we forget the password? How they gonna give us a hint or something like that?
There is nothing about password here. Why are you confusing password? Like, do you want me to explain the picture, the one that there on the screen? Is it like you are talking about asymmetric encryption?
Yes, sir.
Okay, so in asymmetric encryption, I have a key. Like Rachel has a key. Rachel wants to send a message to Alex. Okay. Rachel asks, "Hey, Alex, give me your key." Okay. So Alex says, "This is my key," and that is a public key. So she uses that public key to create an encrypted message like this. Okay. Do you understand that so far?
Oh yeah, sir. Now I can understand. Sorry.
Yeah. So yeah, and then she sends that message. She does not know, right, what Alex is going to use to decrypt that message. She does not know. She has no idea. So even the person who is watching sees this, he cannot know. Only Alex has the key to decode it. That is not a public key. He will not use a public key to decode it. He will use a private key to decode it.
Oh, thank you so much, sir. I was confused, but actually,
okay.
Yeah.
So now let us take. I want you to take a little bit of time to appreciate and understand the quality of the work that was done. Go to Wikipedia and try and understand RSA algorithm, everybody. If you have some time, read this entire thing. It may be hard for you to follow, right? But it is not too. If you are interested in mathematics, you will love this. I loved it very much. Right? I even tried doing this. Even tried doing the encoding, creating prime numbers.
Sir, I'm poor at mathematics.
Okay, so but try and read it anyway. Please read it. Okay. So it tells you the public key, the personal key, how the private key works. It tells you beautiful information about. Am I sharing my screen, right? I'm sharing my screen.
Yeah, I can see.
Yeah. Okay. Yeah. So this is the revolution that was created. It is based on prime factorization. How many of you know what a prime factorization is? You okay? So I will.
No,
Okay.
sir, I'm not. I'm
Okay.
not
So
familiar.
okay. Let me ask you. Okay. Bijay, take two 3-digit prime numbers. Okay.
Sorry, 2 digits or 3
2-digit.
digits?
Yeah. 2-digit prime numbers. Give me a
17.
2-digit prime number.
17.
17. And give me another prime number.
19.
Okay. No, not 19. Give me another like complex one, like 67. 19 and 67.
Okay.
Right? Multiply those two numbers. Right?
I can't. I have to use a calculator.
Okay. So okay, fine. All right. So the way it works is the prime numbers, they can generate this function called totient, right? So you'll take those numbers and you multiply those numbers. That would be the product, right? And then I can calculate the totient, what you call phi of n, by changing those two numbers. Like you can take 19 and 67, right? You said, right? So 18 times 67, I do that, and then I create what I call a modulus. So in this way, I'm able to create a private key. So, and the private key is kept for me. So the way I do it is, I will take these two numbers, right? And then modulus of that number. Modulus means divide that number by the product, and then whatever is the remainder. That is the key that I'm going to share, right? And then that will be and then D, I will keep it as a private key. So just read it and you will follow it very well. But I don't know, if you are not interested in mathematics, probably don't worry about it. But if you are at all interested in mathematics, how RSA algorithm was initially designed, it's all based on math. It's all based on prime factorization, by the way. Okay. So it's up to you how much you want to learn. It's all up to you. You can become a master of this. Right? I mean, this is not like this is not a complex science, by the way. Once it is already discovered, it becomes, yeah, it's easy to follow. But it's up to you how much you want to learn. But this is not going to be asked in the exam.
Yeah.
This is not going to be asked in the exam. I'm not going to ask you, oh, can you explain the mathematics behind an RSA algorithm? That is beyond the scope of learning for this course. But if you are interested, you can learn. Okay, that's what I mean to say. Okay, any other questions?
Sir,
Oh, let me take attendance. I forgot to take attendance.
yeah.
Okay,
So
okay.
like I was going to ask about it.
Ask about attendance. Okay, I'm sorry. All right, but anyway, I'm recording all these sessions, guys, so that like people who miss the class, they can like always go back and check. And one thing that I strongly recommend is, don't just study the course for like, for the purpose of a grade or anything. Just learn it for your general awareness improvement. That is one thing that I strongly suggest to all the students who are taking my courses. So make sure that you are learning it for the purpose of entertainment, right? Learning is fun. In my opinion, learning is fun. Learning is entertainment. So it's like playing a game. Like, you play a game, you talk, you chat with your friends. It's like learning is fun, and you embrace that idea, then you will enjoy learning. Right? Okay, so Jan, can I take attendance? Can you please share? Ahsan? Sanjay?
So your screen is down now.
Oh, sorry. I'm sharing here. Okay. Ahsan? Sanjay?
Yes, sir.
Ashik? Okay, hold on. Reload. Let's reload. Okay. 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 All right. So Ahsan is absent. Ashik?
Yes, sir.
Syed?
Yes, sir.
Farhan? Farhan, are you here? Farhan is absent. Okay. So totally there are 62 students in my class, and I have 60 participants. So only 2 students are absent. So that means I don't need to call anybody's name. I can just put mark present for all the rest of the people. But I need to ensure that these 2 people are really absent.
Sir, I have a question.
Yeah.
So last week I was absent and I emailed you.
Okay, what is your name?
Zuhaib, sir.
Zohaib. Yeah, I will mark it. No problem. Just remind me when I call your name. Yeah.
Okay, sir.
Farhan, are you absent really? Anushka?
Present.
Ghazi?
Present, sir.
Firdaus?
Present.
Yeah, okay. Only 2 people are absent. Prahar? Gurveer?
Yes, sir.
Nareen is here. Deepa is here. Bikram is here. So Rick is here. Alina?
Present, sir.
Subesh is here. Kriti?
Yes, sir.
Bidur? Yeah, I see. Syed Salma. Parashar?
Sir.
Ranjit?
Yes, sir.
Ajay?
So Subesh is present.
Yeah, Subesh is present. Yeah. I'm marking. Please check the screen.
Oh, yes, sir.
Noman? Oh,
Present,
Subesh.
sir. Short answer.
Yeah. Noman, are you here? Noman
Present,
is
present, sir.
present. Yeah, okay. Deepanjana is here. Vinod is here.
Present, sir.
Yeah, Melon. Okay. Yeah, I'm seeing the names of the screens, names of the students here also. So that's why I'm not calling everybody's name, because I can see some of the names of the students. Especially if you have a picture, it is easy for me to remember. Sujit?
Yes, sir.
Samita?
Yes, sir.
Sajicha is here. Arjun?
Yes, sir.
Suraj?
Yep.
Yeah, I think everybody else is present. Only 2 people are missing. Okay, anyway. All right, Rosina? Roshan? Okay, so only 2 people are missing. I see there are 60 people here. All right, so. Oh, yeah. Few people gave attendance and left already. They may be having another class. So if you have another class, you are more than welcome to leave. Sanjog?
Yes, sir.
Shoaib. So Shoaib, right? You were present last class. Yeah. So see, when I don't call your name, that doesn't mean you are absent.
Oh,
So
yes. Another thing, sir. I missed my quiz, so that's why I just emailed you. I think so.
Okay. I will talk about that quiz a little bit later. Yeah. So did you not? Okay. By the way, guys, tomorrow, next week there is a quiz. I message you. Can you please check your messages?
Yes, sir. I've checked it already.
Hey,
In week 9.
Quiz is today.
No.
In week 9.
Week 9. I moved it to week 9 because
Thank you.
Yeah, so I moved it to week 9 so that you have time to study.
So that the quiz is 5% or 10%?
5%. Yeah, all quizzes. Yeah.
So there will be another quiz of 5%?
No. Only totally 3 quizzes, 5% each.
Yeah, so like 2 are more remaining. One is in the week 9 and the last one will be in week 10, 11.
No. There only one is remaining. Only one more quiz, final next week. Last quiz is next week. That's it.
No, sir. So we have only like just let me check, because I attempted only 1 quiz at the moment.
Yeah, but you should have attempted 3 quizzes. 2 quizzes already. 2 quizzes are already finished. Week 4 and week 7, there were 2 quizzes. On week 9, there will be another quiz.
Sir, actually, we are having 3 classes with you, so that's why we are confused in which class we give you the quiz and in which we are not.
Okay. So, but like, see, that's why please check your messages. So next week there is going to be a quiz.
But I'm sure, sir, I missed my last quiz and I email you, and then you said, okay, we'll arrange another one for you.
So, okay, I can arrange a quiz now if you are interested.
Excuse me, sir. In week 4, there